He will be giving the talk on quantum-proof randomness extractor via operator space theory. Let's welcome him.
Okay. Good morning, everybody. First of all, thanks to the program committee and thanks to the organizers for giving us the opportunity to present our work here. So this is joint work with Berta, who's in the audience, and Omar, Fawzi, who unfortunately cannot be here. And it's based on our recent post on the archive. So it will be about randomness extractors. And I would start to remind you about, for those of you who haven't heard about it, for those of you who have heard about it, and just to set up some notation, what randomness extractors are. So we're just talking classical here at the moment. Quantum will come later. And the goal randomness extractor will be able to solve, or will help us here, is that we are going to take a partially random distribution P on a classical alphabet big N, and we want to transform it into a perfectly uniform distribution on a smaller alphabet big M. And the only condition we want to put onto the input distribution is that it contains some randomness as measured by the minentropy, which is just minus the logarithm of the maximal entry of the probability distribution. And first, importantly, we want to do so deterministically. Now, bad thing is that this cannot be achieved. Okay, so this cannot be achieved in a deterministic way if you want to have it that it works for all input sources, given that satisfying this minentropy constraint. However, we can achieve it if we allow the use of an additional catalyst, which will be an additional alphabet big D here, and a uniform random source, so just some uniformly random bits distributed according to this alphabet. And this is usually called the seed, and in the usual constructor like constructions, one tries to reduce the size of the seed, okay? And the best you can hope for is that the size of the seed of D becomes logarithmic in big N, so logarithmic in the input alphabet. Okay, now as I said, the goal of a randomness extractor is to take a partially random source, so a probability distribution defined on N, given that and assuming that it satisfies some lower bound on its minentropy, and it should be transformed into a uniform source, so a uniform distribution, and we demand that this is up to an epsilon in variational distance. So this is just the definition. So we see here, this is the extractor, this is the output of the extractor, so we have some deterministic mapping here, and this is just the output distribution as you would define it. And then we say, well, we measure given the value of the seed S, we consider the one norm difference between the output and the uniform distribution. We take the average over the seed. So that the seed is outside the sum is exactly meaning that we can reuse the seed, so it acts as a catalyst. So we maximize over all probability distribution to satisfy this minentropy constraint, and we demand that this whole thing, which we just define as being C of X and K, is smaller or less than epsilon, smaller or equal to epsilon. So this will be called the classical value of the extractor given K, which gives us the minentropy constraint. Now, that's all nice. Is it interesting? Do we have good examples? Yes, we have. You all know one, which is based on the last over hashing lemma. So that is just a set of two universal hash functions, fs, going from the alphabet n to the alphabet m. And if you define the extractor like that, so just using these functions, and choose the output alphabet big M of size epsilon times 2 to the k, then this actually defines a k epsilon extractor. So for all sources satisfying lower bound on the minentropy in terms of k, you get something close to uniform. Now, extractors are useful throughout theoretical computer science, but this particular example I suggest that they're useful in cryptography too. And especially they're useful because you can just consider the following setting where you not only start with a distribution on n, but you start with a distribution which is initially correlated to some classical, we are talking classical still, adversary on some classical adversary. And still, if we assume that the source is somewhat secure, what will happen is that the extractor, if we let it act just on n, will bring us to a source which is uniform in M and uncorrelated to the adversary. Okay, So you can work out by the definitions pretty easily, and it's already suggested by this example that we take, so the extractor is helpful in actually getting rid of the correlations of the input distribution with some adversary. And this talk is exactly about the question, what happens if we make this adversary quantum? Can we still get that the output is like uncorrelated to Q and almost uniform MM? Okay, for that we need a good condition on the input, and that will be, because, and of course we are dealing with classical quantum states, so which describes a classical source correlated with some quantum system, and the wide generalization of the min entropy to that setting is a conditional min entropy, which is just defined as minus the logarithm of the guessing probability, and the guessing probability is just the probability that an adversary can guess our input, given that he has access to our quantum system Q. Okay, so he can just, this is just P of M, so you can measure the quantum system Q. Now, it makes clear that this definition exactly measures the knowledge an adversary has about our input source, given that he has access about the quantum system. Okay, now we can readily generalize the definition of a quantum extractor to the quantum setting, and we call such extractor quantum proof extractor, which is a K epsilon extractor is quantum proof if we have that this mapping acts, if we acted with it on any CQ state which satisfies our lower bound on the input entropy, this one, that we get something which is in one norm epsilon close to the uniform distribution on M times the reduced state on Q. Okay, and we call this the quantum value of an extractor Q, X, and K, because, well, in comparison to the classical value we had before, which would measure how this extractor behaves in the classical setting. Now Q measures how this extractor behaves in the quantum setting. Okay, so, and obviously the obvious question we want to ask is, what happens if we allow this generalization? So we want to compare the classical value, which, as I said, characterizes what happens if we allow for classical adversaries. We want to compare that to the setting where we allow quantum adversary, and we actually want to understand how this value changes. Now, certainly this value is bigger, or can be bigger than this one, but the question is, like, can we have extractors so that they're equal or approximately equal, or that we can change the K here a bit so that these become comparable? And the obvious motivation is, of course, from quantum cryptography, where we want to use quantum proof extractors for privacy amplification, for example. But in general, we can also think that this is an interesting setting because it allows us to study the power of quantum memory. Okay, we can see that as in the theory of two-partite games, where we either allow entanglement or not allow entanglement. Now we allow quantum memory or not, and we want to understand what's the power of that. Okay. What did we know so far? So first of all, there exist a few constructions which are known to be quantum proof, and especially due to Renato Renner and Thomas Widig, who proved quantum proof properties of two-universal hashing and so-called Trevisan construction. And then this one, the result on Trevisan's work, actually is built on a result of König and de Haal, who show that if the output is just one bit, then the extractors are always stable, also they are quantum proof. However, this behavior is not generic, meaning that there exist examples, one example due to Gawinski et al., which shows that there exist extractors which are classical extractor but not quantum proof extractors, okay? So this example is like, if you formulate it in terms of extractors, actually is a rather bad extractor, so that's rather bad parameter, so you don't want to use it actually in any cryptographic setting. However, it shows that the possibility that there is some question here to resolve. Okay, what is our result? So we want to, as I said, we want to understand that question. We want to understand the question whether, given an extractor, whether it is quantum proof. Or in general, are there any generic reductions for that question? For that, we develop a mathematical framework, which, as the title suggests, is based on operator space theory. So I don't want to say a lot about operator spaces theory. I will give you a hint what it is, or like a short introduction, let's say. But it's really a way, you can think of it's really a way how to formalize correlations between a classical system and a quantum system. And this will be turned out to be useful, obviously, in our setting. So using this framework of operator space theory, we can actually formulate or find semi-definite programs which upper bound the quantum value. Okay, so you may say one of our main results is this following chain of inequalities. Well, this one is trivial. So this is the classical, as we defined, this is the classical value of the extractor, specifying how the extractor acts if we allow for classic adversary. There is the quantum value, which characterizes what happens if we allow quantum adversary. And then we can find an STP which actually upper bounds this Q. And this STP is quite nice. It has nice properties. We can easily handle it. And what is also nice is that actually this STP can be used to show that all known constructions so far are quantum proof. Right? So basically, like it basically gives us a unifying way to prove all the known results about quantum proof extractors. Okay, so like two-dimensional hashing, trivial extractor, what I mentioned so far, you can just plug into this STP, work it a bit out, and you see they are quantum proof. So in some sense, these proofs are even easier than the original ones. In addition, this STP gives us new bounds. Namely, we can show, for example, that if the output of an extractor is small, so the alpha bit has small size, then we can upper bound this XTP like that we have a good upper bound, namely square root m times epsilon. And this you already see, so this generalizes the result of König and Terhal, which means that if the output alpha bit is small, then we get a good upper bound on the STP, and via this inequality I showed you before, we get a good upper bound on the quantum value of an extractor, which means that every extractor is quantum proof as long as the output is small. Okay, so and then this bound is like small. We can also show that if the input entropy is quite high, so that k is like on the order of n, where n is the number of input bits, then the extractor is also quantum proof. Okay, the error behaves nicely. Okay, now think about a moment. We have the situation where we compare classical value with a quantum value. So we have some construction, we evaluate a classical value of it, and we evaluate a quantum value of it. And now we have also this property that we can find an STP which upper bounds the quantum value. So in quantum information theory, there's another like well-known theory where such a chain happens to be, namely this theory of two-partite games. You have exactly the case where you have a classical value, you want to compare it to a quantum value, and you upper bound by an STP. Now, this like similarity is not so surprising, given that we can also show that for every deterministic mapping X on D cross N to M, so we can think of it as being an extractor, we can construct a two-partite game, like a game defined for two players. We have two players, they have inputs, can ask questions, get output, they have to win the game with some probability. And of course we can, as for two-partite games, we can allow classical strategies or quantum strategies. And this exactly corresponds either to the classical value of the game or the quantum value. And now we can show actually that for such a deterministic mapping, this two-partite game which we construct is exactly characterizing the extractor properties of this mapping, meaning that the classical value actually characterizes whether it is an extractor in the classical sense, and the quantum value exactly characterizes whether it's a quantum proof extractor. Okay, so this seems to be a nice connection between these two theories where you study the power of quantum memory. Okay, so yeah, just to repeat, we have like, this is the main question we want to ask. How does the classical value of an extractor behave with respect to the quantum value? And we can connect that to exactly to how the classical value of that game behaves with respect to the quantum value. Now, in the remaining time, I would like to introduce you to the framework, to the mathematical framework we use to prove these results. And to get the main idea really is that we get started and define or see that the if you have a mapping, which is supposed to be an extractor, the question whether it is an extractor or not, so that is again like what is the classic value Cx of k, given that k is the condition we have on the input entropy. This can be phrased as a norm of a linear mapping between normed spaces, or Banach spaces, so to say. Okay, now operator space theory gives us a way how to quantize such spaces. Quantize, I'm going to explain what I mean that with a minute, but it's really a way how to, in terms of allowing correlations between such a linear space and a quantum system. And now, if you take this theory and ask in this theory, what is the wide generalization of the norm of a mapping between Banach spaces? So what is the wide norm of a mapping between operator spaces? The norm becomes something like a completely bounded norm. So you know all know completely bounded norms, or the most well-known completely bounded norm in quantum information theory. It's just if you stabilize the infinity to infinity norm. And this is the generalization of that. And we will see is that much like as the classical value is characterized by a Banach space norm of a mapping, the quantum value of an extractor is characterized by a completely bounded norm between operator spaces. And this allows us to use all the tools of operator space theory to examine the relationship between these two numbers. Okay, so let us start with linear normed spaces. Consider the following norm, just the maximum of the one norm and 2 to the k times the infinity norm. And consider an input distribution P, which has some min entropy lower bound by k, as this just means that the infinity norm is upper bound by 2 to the minus k. We just get that the cap norm is less or equal to 1. Now that means that we can characterize the property of the input constraints on an extractor by just this cap norm. And this suggests, and that you can easily show, that if you define a linear mapping delta x, which is in some sense just, which is just, the first part is just the extractor itself, okay, this is just the adjacency matrix of the extractor, so to say, and this minus 1 over n is exactly the constraint that if you input a probability distribution, it should get mapped to a uniform distribution, okay, if you work it out, if you plug in, so they just define it on a unit vector of r to the r and n, or r to the n, but if you plug in a distribution, you would see that the second sum exactly gives you the uniform distribution. Now, we said that the input constraint we want to have is this one. Yeah, so we want to input all vectors. If we input any vector which satisfies this cap norm constraint, this mapping should have one norm. The output should have one norm less or equal to epsilon. Isn't it? That's exactly our goal, because we want to have this one is exactly the output if we input a distribution. This one is exactly the output distribution. This one is exactly the uniform distribution. So we see that the classical value is just given by this, the norm of this delta x mapping from the cap norm to the one norm, and I just wrote out here the definition, and the requirement is that this is less or equal to epsilon. Okay? So we see that the property, whether this graph, you can think of it as being a bipartite graph, is an extractor, it's just that we write down this linear mapping from r to the n to the r to the d times m, and we can formulate the property of being an extractor, or the classic value, as a bounded norm between the cap and the one norm space. Now, we want to generalize that as a set to the setting where we allow correlations with an additional quantum system. Now, this is exactly the setting of operator spaces. An operator space is defined to be a linear space E together with a sequence of norms on E tensor MQ, where MQ is just the space of Q times Q matrices with complex entries. Okay, this is a linear space, and E has a norm, and we just demand now that we have a set of norm, because E is a linear norm space, it has a norm, and now we just demand that we have a sequence of norm for any Q, a sequence of norms on E tensor MQ. And it should satisfy obvious, consistency conditions. I didn't write them down, it would be a big, short list, but just you can, for example, imagine that if you input an elementary tensor, so think of it as being a product element, something A tensor B, then the norm of A tensor B should be the norm of A in E times the norm of B in usual MQ. And, well, and there are some consistency conditions following from that. Now this is exactly the setting we want to have, because we want to think of a linear space, E, normed linear space, as modeling our classical system, our classical input constraints, and then we allow a correlation with some quantum part MQ. Now, what is the right generalization of the norm of a mapping? Well, exactly, it means that we have to stabilize our mapping in a sense that we are not only interested in what happens if we input something in E, but we are also interested in what happens if we input something in E tensor MQ. So if we have a linear mapping between E and F, where E and F are two operator spaces, then we just take the normal definition of norm between linear normed spaces, but now consider L tensor ID MQ and allow inputs in E tensor MQ, and we just take the sup over all Q. So if you would just put here if you would use as E normal matrices with the infinity norm, then this is just a completely bounded norm you know so far. The dual of the diamond norm, if you want. We call this the completely bounded norm, and you can see that if we restrict Q to just 1, then we get back our normal norm. Now, if you would carry out this operator space construction for the case of the one norm, and you look at the dual space of that space, okay, the dual space is for operator space is just defined as for normal linear normed spaces, then you get something, an operator space whose norm actually characterizes the conditional min entropy constraint. This is not so surprising, because if you start in the classical setting from the one norm, you dualize it, you get the infinity norm, and we just know that infinity norm exactly characterizes the min entropy. So we just do the same in our framework, on this framework, not our framework, in the framework of operator space theory, and we exactly get the conditional min entropy. So it is just like nice, isn't it? We just use the mathematical framework and we get the right thing. Now, using that, we do the same trick as before and characterize the input constraints in terms of a cap norm, which just basically subsumes the constraint on the conditional min entropy as well as the normalization constraint. And now we exactly see that because this exactly characterizes like the operator space be constructed so in such a way exactly characterize the input constraints. If we then write down the definition of the completely bounded norm, also after a few calculations, you see that the quantum value is exact of an extractor, so the number characterizing how the extractor behaves if you allow quantum memory is exactly characterized by a CB norm, a completely bounded norm. Okay. So that means we reduced our question that we want to compare the classical value of an extractor to the quantum value of an extractor, that to the question when we want to compare the bounded norm of a linear mapping to the completely bounded norm of a linear mapping. And this is exactly the right question to ask in the framework of operator space theory. So these guys developed ample of tools to study this question. So we can use these tools to study our particular question whether a classical extractor or extractor which is secure in the classical setting is also secure in the quantum setting. And one of these tools, or a small set of tools, exactly gives you that this completely bounded norm can be upper bounded by a semi-definite program. And this semi-definite program then is in general, it's really an upper bound. So we know of an example such that this one has to be bigger than this one. I'm going to mention it in a minute on the last slide. So, but still, as I explained to you, this semi-def program is enough to understand all known constructions so far. So Trevisan's construction, 2D universal hashing, they all have very nice proofs in terms of this semi-definite program. So, and this is quite easily to get from this completely bounded norm. So again, we reduce the question to compare the classical value and the quantum value to a question whether to compare a bounded norm to a completely bounded norm, and by that we get all these nice properties. Now, some open questions. So I hope I convinced you that the operator space theory is a wide framework to use to study such questions. Now, an obvious question are whether our upper bounds, you remember this upper bounds in terms of STPs, is tight. Mean we get by the STP. So from the STP, we had a generic reduction that any classic extractor is a quantum proof extractor if with an error which behaves like square root of the output alpha bit times the classical error. Now we don't know whether this upper bound is tight. Okay, it can be that this is much too worse. And an interesting example to look at would be the case of random functions. What do I mean with that? I just mean a set. You choose a small set of random functions from the alphabet n to the alphabet m, and you use that small set of random functions to define an extractor, just as in the case of two universal hash functions. Now, this classically, if you just work in the classical setting, it's quite easy to derive that this is a good extractor, like it's almost as perfect parameters. However, if you write down now the STP for this extractor, it's quite large. Okay, so, and this is intriguing because you would think, well, random function is the best what you get. So the STP we wrote down basically characterizes all known constructions which are quantum proof so far, but in the case of random functions, we don't know whether they're quantum proof, and the STP doesn't seem to be the right notions to study that either because it's too big. So I didn't mention that, but actually what we get is a whole sequence of STP hierarchies, much like in the case of in the theory of two-partite games, and we just looked at the first level of that STP hierarchy. And of course, the important question is for these random functions: what happens in the case when we look at the higher levels? Okay, that brings me to my last point. So I mentioned this connection to the theory of two-partite games a number of times in the talk. However, it's just up to now it's just a nice mathematical connection. We don't know yet really how to use it. It would be nice if we could exploit this connection further and use some of the tools of two-partite games in the theory of extractors, and maybe also to understand this example better. And with that, I would like to thank you for your attention.
Okay, we have time for one question.
So there is a SDP characterization of the diamond norm,
yes.
Diamond distance between channels.
Yes.
So there is equality there.
Yes.
What doesn't work here?
So why it does work in the case of the diamond norm is that the input and whereas the output constraints are rather nice. Okay, so the input constraint is just the one norm, and the output constraint is also just the one norm. So what happens here is that because you have this more difficult input constraints where you also condition the min entropy, so to say, then the completely bounded norm is not an SDP anymore. However, actually you can show that the conditional min entropy is an SDP. But if you then use it as if you want to soup over all the inputs which satisfy this constraint, it's not an SDP anymore.
Thanks.
Let's thank our speaker, and we could move on to the second talk.